Hi everyone, just running through the solutions to this week 1 quiz for you. I know I've given feedback for anyone who has completed it, but just working through some of the solutions. Okay, so question 1, we've got a bar chart showing the number of cups of coffee per day consumed by 40 people. The Q3 value is for the variable number of coffee cups per day consumed by these 40 people is... We've got our options there. So we have to find quartile 3. So when there are 40 people, okay, so 40 people means our median, our middle value, will be at 40 plus 1 over 2, so 20.5. So it'll be between the 20th and the 21st person. And then once we've split our data in half, then Q3 will be the middle of the top half. So from our frequencies, at 0 we've got 2, 1 we've got 5, so that brings us to 7, 2 we've got 10, so that brings us up to 17, 3 we've got 15, so at the end of that, we would have 32 people. So our median is in here. Middle of the top half, so we've got 20 people left. You probably don't even really need to find the median. It's just knowing where. Okay, so 40 people in half, 20 people. So the middle of that will be 10.5, so between the 10th and 11th person, and I do from the max. Okay, so coming in from the top end. So in actual fact, we can get rid of that there and go from 10 down. So we've got a frequency of 1. At 5, we've got a frequency of 4, so that gives us 5 in total as a cumulative frequency, plus another 3 brings me up to 8. And so in order to get my frequency of 9, 10 in between the 10th and 11th person, that means the number of cups of coffee for Q3 is going to be 3. Okay, question 2, a table listing 10 major producers of uranium in the world and their production in thousands of tonnes in 2016 is shown below. The number of outliers in this data is. So in order to calculate your outliers for our lower boundary, that means we're doing Q1 minus 1.5 times the interquartile range. And for our upper boundary, we're doing Q3 plus 1.5 times the interquartile range. So we don't know whether there'll be an outlier at the lower end or the upper end or both. Given that we only have 10 countries, so there's 10 values here, it probably is quicker to put that into our calculator and do a quick check for outliers by looking at a box plot. So let's do that now as a bit of a reminder. So a reminder, when you go in, you are going into lists and spreadsheets. We need to give our list a name. So we're talking about the production of uranium, and then we're just listing the values. So we're just listing them as we see them in the table. There is no need to reorder them, and we don't need to list the countries. It's just the numbers that we're talking about. Okay, we're looking at univariate data, so no need to do anything other than the numbers. Okay, once we've got those in, we could do our summary stats and get the Q1, Q3, calculate those, but I think for a multiple choice question, you want quickest and easiest way. So I would add in a data and stats page, put in my variable so I can see my graph. I think this is going to be an outlier up here, that dot 24.6, but there potentially is that 410 as well. The way we can check for sure if we go into our plot type and draw a box plot, remember your calculator will automatically show them as outliers. So there we go. We've got 2 outliers in that data. And so then coming back to our options, we can then select 2 as our answer. Okay, question 3. The heights of boys in an under 12 soccer competition are approximately normally distributed with a mean of 153 centimetres and a standard deviation of 7. So when you see that approximately normally distributed, that's where you're thinking about bell curves or Z-scores. They're the 2 things that relate to normal distributions. So Fawad and Vin both play soccer play in the soccer competition. Fawad is 140 centimetres tall and Vin is 165 centimetres tall. So which of the following statements is true? And if we look at the options, we can see they're all talking about these standardised heights. Okay, so we are going to need to calculate the standardised score or the Z-score for both of the boys. So for Fawad, and remember your Z-score is your actual minus the mean over the standard deviation. And note they've given you both of those things as part of the question, the information. Okay, so Fawad, we've got his actual height of 140 minus the mean of 153 and divide that by 7. When we do that, so 140 minus 153 and then divided by 7, we get negative 1.86. Then Vin, his actual height 165 minus the mean of 153 over 7. Now this time his value should be positive because his height is greater than the mean. So remember the mean is that 0 line, okay, when we're talking about those standard scores. So 165 minus 153 divided by 7, we get 1.71. So now that we have that information, we can work out which of the options are true. So I tend to write T for true, F for false, because if I tick and cross, I can accidentally get mixed up. Okay, so standardized heights for Fawad and Vin are identical. False. We can see they're different. If Vin's height was increased by 1 centimetre, he would have a standard height value that is the same distance from the mean as Fawad's. So we need to check this because if Vin is increased by 1 centimetre, so if his height becomes 166, his Z-score will increase because he's getting further away from the mean. So if we check that value just quickly, or we can even just judge by Fawad is 13 below, and this will be 13 above by the look of it. So 166 minus 153 divided by the mean of 7 gives 1.86. Okay, so that appears to be true. Let's check the rest though, just to make sure. If Fawad's height was decreased by 1 centimetre, so now we're decreasing instead of increasing, and Fawad's height. So that would mean his height is getting further away from the mean, so 139 instead. He would actually get further away, so his Z-score would still be negative, but the number itself would increase. Okay, so that's going to be false. I don't need to calculate it. Vin's standard height of negative 1.71. Already not true. And Fawad's standardized height value of positive 1.71, already not true. That's Vin's. So therefore we can see that option B is our best answer there, correct answer. Okay, question 4. The histogram below shows the distribution of gross domestic product per person in dollars per year for a sample of 27 Asian countries in 2016. Using the histogram, the percentage of these 27 countries with a GDP per person of less than $20,000 is closest to. So less than 20,000, we're talking about this group. Okay, so working out our frequency there. We can see that we've got 2, 2, 9 and 6. So when we add those together, we've got 19. Okay, so 19 countries. But this is asking for a percentage. So we have to do 19 out of the 27 countries and multiply by 100. So when we do that, so 19 over 27 times by 100, we get 70.37. And so out of our options here, that gives us D, 70.4. Okay, the following information is for questions 5, 6 and 7. So here we've got statistics to apply to the maximum temperature in degrees and the average gas use in a home in megajoules per day during September, recorded over a number of years. The distribution of maximum temperatures in September is normally distributed. So again, that points us towards the bell curve and Z-scores. And the amount of gas use can be predicted from the maximum temperature. So that implies that the max temperature is the explanatory variable, and the gas use is our response variable because it's been predicted from the explanatory. Okay, so that might come in handy if we have to do any work about interpreting what's going on. So make a note of that. So temp, EV, gas use, RV. Which of the following statements about the maximum temperatures in September is not true? So being really careful. 84% of the maximum temperatures would be above 13.6. Max temperatures, so here we're starting to see standard score, 68%, 84%. So these are all values that relate to our bell curve. So that's where you want to go to the diagram that you'll have versions of in your notes, in your bound reference, ready to go. And you want to fill in the intervals. Okay. So in the middle, we put the mean. So we're talking here about the max temperatures. So we're going to use the mean and standard deviation from that. So the mean 17.2. And then we're going to add on, so 17.2 plus the mean, the standard deviation, 3.6. So 20.8. We add 3.6 again, 24.4, and finally add 3.6 again, we get 28. Then we'll do the same thing again. So 17.2, but this time minus 3.6, we get 13.6, again 10, and finally 6.4. So now it's about working out what matches. The other thing that you need in this diagram, and that's why it's good to grab the one that's in your notes, is those breakdowns. So you've got what percentages go where. And I can probably remember most of it, but I'm just going to check. So in 15, 235, 0.15. Okay, so now we can sort of go about working out, well, what does match? So we're looking for things that aren't true. 84% of the maximum temperatures would be above 13.6. So this is referring to this section here, okay, above. So working out what falls there. Knowing that halfway you get 50% plus another 34, so that would be 86. And so that is true. A maximum temperature of 24.4 would have a standardized score of 2. So again, off our diagram, A standardized score of 2 means plus 2 standard deviations above the mean. And so 1, 2, yes. Okay, that is true because it lines up with that interval, that line. 68% of the maximum temperatures are between 13.6 and 20.8. So 68% is this middle band here, 1 standard deviation either side, 13.6, 20.8. Yes, that is also true. 13.5% of the maximum temperatures would be between 24.4 and 28. So looking at where's 24.4 and 28, that's here. And yes, sorry, not there. Next one across, here. But we can see that's only 2.35%. So that one would be false, but we'll just make sure and do the last one. 0.3% of the maximum temperatures would be above 28 and below 6.4. So below 6.4, above 28, yes, that's that 2 lots of 0.15. So added together would be 0.3. And so that gives you your answer is D. So there you can see you're combining both standardized scores and the normal distribution. Having that template that you would have had in univariate data, if I just flick to one of those, these templates, super important. So you might want to print out some blank ones so you've got them ready to go for your exams and to use for your exam revision. Okay, question 6, so leading on with the same information, the equation of the least squares regression line for this relationship is closest to. So first thing, we said the maximum temperature was the EV. So that means that the last two options are not possible. So we can cross them out, okay? Because the order of the variables in the equation is not correct. The second thing, when you get information in a table like this, you want to go to that section in your bivariate data notes. And so if I just jump to that now, where you are doing your least squares regression line using the summary stats. So it's using these formulas here. Okay. So first thing that we need to do, let's go back to the question. We can see here that the slope or the gradient, the same value each time. One thing that is different is the sign. So if we look at the summary stats, the R value of negative 0.6 means that I have a negative relationship. Okay, so that means I can also knock out C. The only difference between A and B is the value of the y-intercept. Okay, so using our formula for our y-intercept, so A equals the mean of y minus B, so the slope, times the mean of x. So we still need to use, but we've got it in the formula here. So we actually don't have to calculate it. So the mean of y, remember that's our gas. So going back to the table, mean of gas, 34.1. Minus the slope that is common to both, so negative 1.4 times the mean of y, and our mean of y was 17.2. And so popping that all into our calculator gives us a value of 58.18. So closest to A as our answer. Finally, question 7. So the value of the correlation coefficient R for this relationship indicates that. So we're looking to match what the sentence is. So our R value was negative 0.6. So as we said, that already tells us that we have a negative relationship. Okay, if we read through, so as the maximum temperature increases, the amount of gas use will also increase. You can see it's opposite. So as the temp, remember we said the temperature was our EV, as the temperature increases, our gas decreases. 60% of the variation in the gas use can be explained by. All right, when you see variation explained by variation, that is actually referring to your R squared value, the coefficient of determination. And that isn't 60%, okay? It would actually be that 0.6 squared, okay? So that would actually be 36%, okay? So R squared is 0.36, not 60, so not correct. As the temperature increases, people will need to use less gas. So that's a possible answer, but we need to be really careful about the language. Remember, we're talking about correlation, not causation. So let's check the rest of the options to see if there is a better version. D, 36% of the variation in the maximum temperature can be explained by the variation in the gas usage. So again, looking at the structure, variation in the maximum temperature can be explained by the variation in the gas. The order, so the tricky thing here is that this time it's got the right R squared value, but our sentence should be the variation in the response is explained by the variation in the explanatory, okay? So it's actually the wrong way round. Finally, an increase in the maximum temperature is moderately associated with a decrease in the gas usage. So 0.6, moderate relationship. This time they're talking about an association rather than definitive language of will need. So this is a better answer than option C. So it is a tricky one. All right, and you want to be on the lookout for that sort of definitive answers. You be really careful you don't get caught out by those. Okay, question 8. So the value of Bitcoin has increased rapidly during 2017. The value in US dollars of each Bitcoin on the 20th of each month during 2017, correct to the nearest dollar, is shown in the graph below. The graph is clearly non-linear. The best transformation to linearize the data is. So here we want to look at our graph. We can see, yes, it definitely has that sort of shaped curve to it. So that's where we want to go into our bivariate notes and look for our transformation circle. Okay, so looking at this one here. So our options, log y, so log of the vertical axis, 1 over y, or x squared. So let's go back. So we said log y, 1 on y, or x squared. So of the options, well, it's not linear, and we're not going to use a linear relationship to transform. Log of the value axis, value is what's on y, so that is appropriate. A reciprocal transformation, remember reciprocal is the 1 over, and they're saying 1 over month, which would be 1 over x, not an option. A squared transformation of the value axis, that would be a y squared, not an option. And a logarithmic transformation of the month axis, so log of x, again, not our option. So our value there, or our answer there of B, log of the value axis is our best option there. Okay, question 9. The least squares regression line for the relationship between the value of two cryptocurrencies, Bitcoin and Ethereum, in US dollars is shown below. So we've got our equation there. When the Bitcoin was worth $2,044, there was a residual value of 2687 from the least squares regression line prediction. A bit of a mouthful there. The value of the Ethereum at the time would have been closest to. So here we want to go back. We want to use, I guess, our knowledge of residuals, okay? So remembering that our residual value, the way we calculate that is by, is always by our actual, so our actual value, Y value, and our minus our predicted. Okay, and we're talking about the Y values, so we're talking about Bitcoin. So the actual Bitcoin value was 2044. The residual value, 26.87. So we can use that to find what the predicted value was. Okay, so we don't know predicted. And then once we know what the predicted value is, we can use that in the equation to work backwards and find the Ethereum value that must have been substituted in. So we do that, our predicted Bitcoin will be $2,017.13. And then putting that, so 2017.13 equals 285.43 plus 1872 times our Ethereum, and solving this. Okay, so we would jump into our calc and solve. And what we will get is that our Ethereum is equal to 123. And so that gives us option B. So that's quite a challenging question, particularly when you haven't really done too much revision, but that's sort of letting you know that's the standard that they'll be asking that sort of question at, even in a multiple choice. Okay, question 10. The time series plot of Etsy's revenue in millions of dollars is shown below. Which of the following best describes this time series? So here we've got our time series graph, and remember when we're describing our trends, we're looking for a couple of things. So do we see any general upward increasing or downward decreasing? And yes, definitely here we can see there is a general upward trend in that time series data. The second thing we then look for, is there any patterns of behavior? And so we should hopefully be able to see that we are getting a bit of this sort of wave. Now it's increasing each time, but the thing that we are concentrating on is where these peaks are they the same distance apart? So checking, they're all in line with Q4. So we have a cycle that is occurring, and these gaps between each peak in the cycle is 1 year apart. So remember, if it's 1 year or less, then it becomes seasonal data. So out of our options, cyclic with increasing, we can better describe it. Increasing with random, no. Seasonal with no trend, no. We've definitely got an increasing. So there we go, seasonal with increasing trend best describes. An increasing with structural changes. Remember, structural changes would be something where our data is traveling along and then something big happens. Okay, so stock market crash, natural disaster, weather event, all the different things like that. The collapse of a company, will it impact sales, all that sort of stuff. Okay, so that's what your structural change is, massive change in the general pattern. Okay, question 11. Etsy's quarterly profits have been determined to be seasonal over the period of 2013 to 2016 inclusive. The seasonal indices for their revenue in millions of dollars are shown below. The least squares regression equation predicts that the deseasonalized sales, so really important, is given as there's our equation there. So where Q1 in 2013 is time code 1. So remember, we have to attach a time code. So we can substitute into the equation. Etsy's actual sales in millions of dollars during the first quarter of 2017 is predicted to be closest to. Now here, we can use the equation to get the deseasonalized sales, but then we have to use the index for first quarter to then go back to the actual sales. So there's two components here. All right, remember our deseasonalized value is the actual value over the index. So step one, let's find the predicted deseasonalized sales, okay? And so that will be, so our DS sales will be our 20.13 plus 4.72 times. Now our time code for the first quarter of 2017. So first quarter of 2013 is 1, of 2014 is 5, 2015 is 9, 2016 is 13, and 2017 will be 17. So we're substituting in 17 there. So you've got to count forward to get to the number you've got to substitute in. When we do that, we end up with a value of $100.37. So that's our deseasonalized. Sorry, and this is in millions of dollars. So 100 million. That answer is there. Don't be tricked though. This is the deseasonalized. So the second layer of that is to find the actual sales. Okay, because you've got to be really clear and careful what it's asked for. So our actual sales will be our deseasonalized times the index. So 100.37 times our index of 0.86, and there we get 86.3 million. So A is our answer there. Okay, final question. The seasonal index for sales of cold drinks in a shop in July is 0.54. To correct the July sales of cold drinks for seasonality, so to correct for seasonality, the actual sale should be. So you want to look for that little section in your bound reference about how you correct for seasonality. Okay, when you are looking at that, so all the way down near the bottom of our section for seasonality, we have this bit about correcting for seasonality. Okay, so 1 over your known index minus 1 times 100. So it's not as simple as going it's 46% below. We have to do 1 over our known index minus 1 and then times 100 to get the percentage. And if I get a positive number, it tells me I have to increase. If it gets a negative number, I have to decrease. And so when I do that, so 1 divided by 0.45 minus 1 times 100, I get positive 85.16. So that means I need to increase by and closest to 85%. So E is my answer there. Okay, that's it for these solutions. Hope that helped.